Hello, I'm Kelsey Breseman, and I'd like to talk to you today about the decentralized web. And I'd like to ground this in a little bit of history, in this case, in a very good rant that was written by Tim Berners-Lee on a style guide in 1998, which rather famously had the quote, "Cool URIs don't change." And the concept in this quote was that not only is a changing URI annoying and hard to track, but when you give somebody a link and it breaks, you can lose trust in the server and whoever controls the server, and you may no longer use that resource. In fact, Tim Berners-Lee wrote that part too. Really, go read the rant. It's pretty great. And in my work, I come into this question with, what if the owner of the server is your government? I work at the Environmental Data and Governance Initiative, which is EDGI for short, and what you're seeing here are the covers of several of our reports. EDGI came together because of a fear that environmental data that is held and basically entrusted to the public by the American government might come under some threat in an anti-science, anti-environmental presidential administration. And I would like to be clear here, like, this is not necessarily a political, like, one side versus the other thing, regardless of who wins an election or who holds power. I would like for there to be a group, us in particular, tracking these sorts of things. But what you see here are the reports over the Trump administration, which is so far the duration of this organization, taking a look at how stewardship of environmental data has changed through this administration and how that has borne out in terms of health effects, in terms of being able to have the public be informed about public policy changes that they might want to weigh in on, and other things in this area. And one of the things that comes out of these reports is that we look at, we programmatically scan through government websites and we categorize different changes. And this is one that we found. This one, you may notice the change as well. It's fairly dramatic. This is March 1st, 2017, a Climate Change Clearinghouse, and this is January 27th of this year. This website is gone from this URL. And when this happens, you have a couple questions that come to mind, right? One is like, is this saved anywhere else? If it is saved somewhere else, how would I find it if I even think to look for an archive? If I do have an archive, how can I know that it's trustworthy? So like something on a .gov domain is considered to be inherently trustworthy, or by most people. But if it's on like my personal domain, you might look at that and say, okay, well, she says that it's from a .gov domain, but how do I actually know? How do I know that I can trust this? And not just me trusting it, but how can I base my scientific, legal, or policy work on this data set that's hosted on this random person's domain? Because they might not have legitimacy to say, okay, yeah, this is something I can trust, this is something I can really believe, this is something that I can back up. And then finally is the question of, is the archive any safer than the original? So like, say I did personally archive that site, and then I forgot to pay my DNS server one day and my site's down, or like I take a trip and decide that I no longer care about websites, whatever it is. Suddenly maybe that access is gone, or maybe you relied on the .gov one and then you relied on mine, and then you tried to you didn't know it was also hosted a bunch of other places, but you didn't know where else to look. So these are all problems that bring me to the study of the decentralized web. And this is a really interesting field, and there is a lot of really good blog posts out there and video content and tutorials, and I invite you to follow up with those if you find this interesting. What I have for you today is what I think is the most accessible version of, assuming you come in with no knowledge about the decentralized web, I think I can get you up to speed with the basic terms and how it works and why it matters. And this is based on a collaboration I did with my sister, actually, last year, where she and I went in and tried to parse out the simplest bits of this that we could. So let's say we want to put some files on the decentralized web. Let's say this file. And let's say that's what this is what's in the file. We have a little text file, and PNG, and we have a survey.csv file that's a little bit bigger. So the first thing we're going to do is chunking or standardizing. When we do this happens automatically when we upload this to a decentralized web file storage. And basically what it does is break up the files into a specific chunk size. And what you can see here, you can kind of make this metaphor that you're trying to fit the files into a box. And if the file's too big to fit in that box, you might put the leftovers in another box. But you wouldn't combine files in multiple boxes. And this uses the standard from IPFS, which is 256 kilobytes. So you can see that based on this chunking, we have now our 3 files are turned into 4 chunks in order to fit into that standard file size. So why is it useful to do this chunking? A couple of reasons. Basically, a standard is helpful, and a small standard is particularly helpful because what you can do is estimate the maximum file size that you're working with. And you can use that to look at download speeds, you can use that to say if it's going to fit on your hardware, and various other benefits of just being able to know the maximum amount. The next thing we'll need to do is hashing. And you can think of this as putting a label sticker on that file box. And the label sticker is not going to be that legible to you and me, but it will be legible to your computer, and that's what matters in this circumstance. This whole process, by the way, does happen behind the scenes when you use IPFS or DAT or any of the other protocols that do file decentralization. So we're going to put this label on through hashing. And this is really cool. The label is actually a hash of all of the contents of the chunk. And what that means is that all of the contents of the file, including metadata, are typically fed into an algorithm, a hashing algorithm, that produces this identifier. And it has a few important characteristics. One is that this is one way. You can't use the output to back derive what the input is. This is a security measure. And the example over here on the side shows, for example, if I got the output 4, I wouldn't be able to tell whether the input had been a 4, a 9, or a 14. All of those would produce that output 4. This example is not the one that's actually used, but it is a little clearer than a hashing algorithm that would be in use here. Another important characteristic is that a hash would have a fixed size. So, much like we were talking about with chunking, it's important to have things be a maximum size for various reasons of speed, of standardization, and that's one thing that is a characteristic of a hash in this system. So you can see on the right here, a single word and a sentence using that same word both end up with the same size of hash. A hash is deterministic. If you put the same thing in, you should get the same thing out. But it's also collision resistant. If you put a different thing in, you should get a different thing out. So let's say we've gone through that process. This is using IPFS's hashing. And so now each of our chunks is labeled with a hash. And again, you'll notice that survey.csv, because it's in 2 chunks, gets 2 hashes. So I touched on this a little bit, but one of the major reasons why you would use hashing as a labeling system is that any change anywhere in a file will result in a different hash. So if you change even the metadata, or if you change one period in one part of one file, because you're feeding the entire file into the hashing algorithm, that change is going to show up as an entirely different hash. So this is tamper-proof. Well, I hesitate to say anything is something proof, but you get what I'm saying. It can also be used for identification, as it is here, because the given hash will always return the same file. And it's efficient. Even a very large file can be identified with short text strings. The next thing we're going to do is hashing things together through what's called a Merkle tree, or a directed acyclic graph, a DAG. So, in short words, this is turning all of those labels into one label that says, hey, these things go together. And here's what that looks like. You have all your hashes. You copy and paste the two next to each other into one text file. This text file is now content that can be hashed. So you hash it. And then you do that again until you only have one. And what's cool is now that you have this one, you can decode it. You can ask for the original text file back, and you know that it splits into those two hashes, and so you can use that to go the other direction and get your files back via their identifiers. And as you can see, it has basically the same benefits of hashing. You use one hash to find all the data that's related, so that's why we want, this entire folder now has this one hash, so that's very efficient to be able to pass around. And you can put an entire library through that Merkle process, and you can say, hey, this is this library. So now you have this identifier that says this is this very specific file set. And you can do this verification process. And this is really cool, and I talked about this a little bit before, but you can see it here. If I modified this one chunk, the second part of the survey.csv, that change is going to propagate up through all of the files, meaning that they all have different hashes. Here, if I go back and forth, you can see that the hashes change. You can also do partial verification. So if you don't need all of the files, you can say, okay, well, throw out that survey CSV. That seems like it's been tampered with. I just want to get the summary and the image. You can still do that in a fully verified way. Now, finally, we want to access these files. You're going to request their URI. So this is another Tim Berners-Lee quote from the same rand. A URI, by the way, versus a URL is Uniform Resource Indicator rather than Uniform Resource Locator. And that's best explained by this quote, I think. What you need to do is have the web server look up a persistent URI in an instant and return the file wherever your current crazy file system has it stored away at the moment. The paradigm here is not to say, I want you to look in this place and return the file that's there. The paradigm instead is to say, hey, I want this thing, get it for me wherever it is. And that is what DAT and IPFS do. And typically on IPFS, the URI will be the top level hash, the one that we got through that Merkle tree process. So you'd go out and request over an IPFS browser or an IPFS client. IPFS does its magic algorithm, finds all the different chunks. Different chunks can come from one person or from multiple people. And it comes back to you as that top-level hash. Because files are found by their hash, you will always get the exact same content back. So any modification of the file, I know I'm beating a dead horse here, but you'd get a totally different URI if anyone had changed any part of that file, which works really great for my purposes of archival work. So IPFS is really strong for static content. Another protocol that's in pretty common use is DAT. The URI is the read key for the directory. So if you're using an SSH key pair, you'll have the private key and the public key. The public key is the URI. So if you supply the URI of that public key, it's going to say, okay, give me content that was published by people who are authorized using that private key. So we know who it comes from, we don't know what it is necessarily. And so they'll go out and they'll ask, okay, what's the latest thing from this authority identifier? And then across the network, it will compare date stamps of different things that correspond to that public key or chunks of things that correspond to that public key. It will say, okay, here's the latest, and here it is. Because files are found by their read key, you will find the most current content available. So more practical for example, a blog or other content that might change. The URI will not change in this process. And then, once you've got the file, assuming you're running DAT or IPFS servers, you're able to be a host and reshare it out to everybody. So when you download data, you will automatically rehost it, and you'll be able to share files or chunks, just like on if you ever used LimeWire or BitTorrent or any of these types of clients. It shares across peers on your network, which makes you a node, and it strengthens the full decentralized web. And it particularly strengthens the network that's able to supply the documents that you have that you've requested, which means that popular files are much more likely to be safe. So, for example, if something off of that climate clearinghouse was used by a lot of scientists and the .gov page went down, if everybody was using the decentralized web for it, it would possibly not be that important because it could be accessed from any number of users. So, returning to my use case, this is a particular use case that came onto my email last year. Someone reached out to my organization and said, hey, we have an issue. There was a big fire in Deer Park in Texas. And there's all this data that is about the air quality monitoring in the area. We know that the fire was really bad in terms of releasing benzene. We know that in a decade or two, that benzene is very likely to have major health impacts on people living in the area, the people who went back to the factories right after this explosion due to poor handling on the ground, and the children who went back to school in the area. We need to make sure that this data will be available a decade from now when those health impacts begin to show up. And so they were requesting that we find a way to securely store this because they were worried that there might be some conflict of interest. Specifically that the people who held the data might also be the people who would be held culpable in a legal case about the data, using the data. That's an issue. So this is what some of this air quality monitoring information can look like. There's like all this data about different places, different moments, different chemicals, all this sort of stuff. And I'm not an expert on it, so we looked at these files and said, oh, shoot, what do we save? And we tried to save as much as we could, structured data, PDFs, maps, whatever, using their guidance. And we saved it in two different ways. So I used this example. We saved it in two ways. One of them was we worked with our partner, the Internet Archive, who maintains databases in a physical server set in San Francisco. And the other is that we stored them with a partner IPFS, or a partner Query whose business is to store data sets, structured data on IPFS. I actually have a paper out this year that contains this quote about this. Data were considered to be at risk unless they had a dedicated plan to not be at risk. This is from a study that we did with various archive managers, librarians, other people saving data, about concerns around preservation. People have this idea that if you put something on the internet, it's there. That's not accurate. And if you talk to the people who are managing that stuff, it's so easy to lose data. And in this paper, what we did was we devised a risk categorization matrix to try to help data managers understand how specifically their data stores might be at risk and how they might prioritize mitigation strategies. So I applied those strategies, or I applied this risk matrix to our storage of these Deer Park issues. And so this is data risk for PDF stored in a traditional archive. And you're welcome to quibble with my metrics if you'd like, but basically what you can see, catastrophes, severity of risk could be pretty high, especially if we're storing it on a fault line in San Francisco. Time to recover, high in this case might mean never, right? Like if the data is erased from the only place that it is, it's gone. But other things, it's really good. So if it's not used very often, the severity of risk is low. You put it in an archive and it probably sticks around. You can see that putting the same files on IPFS provides a pretty different risk matrix profile. And I'll toggle back and forth just so you can see like the colors move. You can see that this is, in theory, and this is under the assumption that this is well distributed across people and servers, the catastrophe metrics are all very low. On the other hand, lack of use is much higher as an issue because the main thing that might happen is that nobody downloads this and therefore it's just not really available as a node, at which point it's just lost. But this is sort of the promise of the decentralized web. what if traditional archives were adopting decentralized webs kind of across several platforms, across several locations and servers? That's when you could start to have the benefits of both systems. And you could be much more confident in the maintenance and curation of data that might be at risk. In summary, single point of failure risks are down and new technology risks are up. And I'll just kind of leave you with this. The best way to strengthen the decentralized web is to use it. This is early technology, but if you try, for example, Beaker browser for DAT, or if you install an IPFS client on your browser, you can already begin to use this, and it's pretty straightforward to begin playing around with files in this space. So check it out. Thanks for listening, and credit to my sources here.